Okay, hello everyone. So this is the first part of the fourth lecture, and today we talk about random experiments and differences. You see, we have quite a lot of slides, but we have very little math, at least as compared to the last lecture. So let's get started. So I put a couple of references here, especially concerning the differences design. But let's jump right into the treatment effect literature. Yeah, so kind of like when we talk about treatment effects, we think, for instance, of a binary treatment, and the classic is a medicine or job training, scholarship, teacher training on an outcome variable of interest. And like, for instance, for medicine, we look at the health status. For job training, we maybe look at your unemployment status. Scholarship, you look at academic achievements and this kind of stuff, right? And we have some sort of a random sample. And now for each individual, we of course observe the outcome and we know whether or not this person has received treatment. So this DI is the treatment indicator, which is 0 if you do not receive treatment, and it's 1 if you have received the treatment. And then we talk about the so-called potential outcome. Yeah? So kind of like the causal treatment effect literature is actually based on this potential outcome framework, which is surprisingly recent. Yeah, so it's from the 70s. And we say that YI1 is the potential outcome of an individual that gets the treatment, and YI0 is the potential outcome of the same individual if it does not get treatment. And if you kind of look into the references, there's several notations for the same things. Yeah, so for instance, here, YI, the 0 in brackets, it's the same thing as this thing, for instance. Yeah, so, and as you also see, kind of the kind of language that we use in this literature is often borrowed from medicine. Yeah, so when we talk about treatment and control groups and this kind of thing. Okay, now the big problem, of course, when we want to kind of assess the effect of a treatment is that we cannot never simultaneously observe both potential outcomes. Yeah, so kind of like if I have a patient in medicine and I kind of treat that patient with a certain medicine, then I can only see this. Yeah? I don't know, and I cannot observe anymore what would have happened to the same person had I not given that person the medicine. Yeah? So we cannot observe the counterfactual. We cannot know what would have been in the absence of treatment. Okay, so that is bad, right? So we can never identify the treatment effect on the individual level, because for that, we would have to see both potential outcomes, which is not possible. Nevertheless, we may still be able to kind of identify the effect that the treatment has on average. Yeah? So kind of on an average, on a random individual taking from the population. Yeah? And this is one of the objects of interest in this literature. So we kind of look at the average treatment effect, the ATE, which is simply, as you can see here, the average, like when we take the expectation of the potential outcome under treatment relative to the potential outcome in the absence of treatment. Yeah, so kind of really it's the kind of average in the sense that if we randomly pick an individual from the population, this ATE would be kind of like our best guess for the treatment effect. Okay, so we have talked about the average treatment effect, but in the literature, you will also see this thing here, the average treatment effect on the treated. Yeah, so the difference is that here we really focus on a subpopulation. Yeah? We don't consider the whole population that we do in the average treatment effect, but rather we focus on the subpopulation of those individuals that actually participate in the treatment. Yeah, so and this, of course, a smaller subsection of the whole population, and only under certain assumptions. Yeah, kind of, for instance, that the treatment is the same also for those people that do not receive the treatment. Yeah, so kind of we make this constant treatment effect assumption. Under these assumptions, you can say that the average treatment effect on the treated is actually the average treatment effect. Yeah, so let's say kind of you look at the effect of military service on wages, then the ATET would actually consider the subgroup of the population that actually does military service. Yeah, whereas like the average treatment effect would again kind of measure the treatment effect if you were to pick a random individual from the population. Yeah, and of course, like in certain examples, the actual object of interest may be even the effect of the subgroup. Yeah. So for instance, consider a job training where you specifically target people that have, for instance, a low level of education and that are likely to be long-term unemployed. You want to really know what is the effect of the treatment in this term, in this case, a job training, on this particular subgroup of the population. Yeah, right. You don't really want to know what is the effect of the same job training of like the people that already have a high paying job, yeah? Because you really want to target a particular subgroup with a treatment. Okay, so now what's the problem? Again, we said that we cannot observe the counterfactuals. So we don't know what would have been the case for that particular individual had that individual not received the treatment. Now we could try to do the same, like basically to estimate the average treatment effect by naive comparisons, right? So we simply take the average outcome of the treated. Yeah? So we look at the subgroup of the population that has received treatment. This is what we indicate with conditioning on the treatment indicator being 1, right? So you see the average outcome of this particular subgroup of the population to the average outcome of the non-treated. And you see that here we condition on the treatment indicator being 0. Yeah? So here we have the average outcome of the non-treated. Yeah, this is kind of like the remark in the second line. And now the question is, of course, does this naive comparison make sense? Are we actually measuring what we want to measure? Yeah, and just to give you an example, let's see, we want to assess whether hospitals actually improve average health. Yeah? Should we kind of, are hospitals actually useful? And if you look at simply the data, the raw data, we see that kind of people that go to the hospital here, the health status is 3.21. And people that do not go to the hospital, the health status is 3.93. Right, so kind of what would be the naive treatment effect for going to an hospital? It would actually be negative, right? So your health status is lower if you are in a group that goes to the hospital. And right, if you interpret this naive comparison as if it was measuring the average treatment effect, the outcome of your experiment would be, well, get rid of the hospitals. Now, it is very clear that kind of this naive comparison, that's why it's called naive, does not really make sense, right? Yeah, so if we simply take the observed average outcome in the treated group versus the non-treated group, we are probably making a mistake here. Yeah, so let's kind of let's analyze this. Now, the observed outcome can be written like this. Yeah, so kind of when the person is untreated, it is simply this, and DI is 0. Yeah? So this whole thing here drops out. And if the person is treated, then it's this plus, DI is 1. And it turns out that this cancels with this, and we have the YI1 here. Yeah, so indeed we can write it like that. And now let's plug this in. So this is our naive comparison. And now what we do is we simply replace the YIs with the right-hand side. Okay, that's kind of what I'm doing here in the second line. And now what you should notice here is that if I condition on DI being 1, then I can set this thing to be 1. Yeah, so it's the YI1 that stays here. Everything else drops out. And here similarly, kind of since we condition on DI being 0, there's the YI0 that stays here. And then kind of what we're doing here is that we are adding and subtracting this term here. And why are we doing this? Well, because this term is giving us something sensible. This is the average treatment effect on the treated. Yeah, so you see that kind of here we have the potential outcome under treatment versus the potential outcome without treatment in the subgroup of the population where the treatment indicator is equal to 1. This is really the definition of the average treatment effect on the treated. And we see that our naive comparison gives us something sensible plus something that we don't like. Yeah? So this is the selection bias. And you see here kind of that the baseline, in our hospital example, the baseline health status in the treated versus the non-treated is different. Yeah. So, okay, I think here kind of we discuss what happens. Yeah, true. Yes. So again, the average treatment effect on the treated, we look on the subgroup of the population that receives treatment, that goes to the hospital in our example. Yeah? And two problems here. First of all, we can not observe this thing. Yeah, this is unobservable because we cannot observe this, right? So you see here, we are looking at the people that receive the treatment that are going to the hospital, but we want to observe their average potential outcome without going to the hospital. That's impossible. And similarly here, right? We want to look at the people that go to the hospital, but we want the yi0. Impossible. That's a counterfactual. We cannot observe this. So that's the problem. So we can neither really observe this nor this. Yeah, so we cannot disentangle them because we cannot observe either of them. And in our hospital example, it is pretty likely that the actual effect of the treatment on the treated is positive. Yeah? So if you're sick, you go to the hospital, it's likely to improve your health status. However, the selection bias makes the whole thing negative. Yeah? So, and it's very clear, very intuitive why this happens, right? So those people that go to the hospital, they go there because they're sick. Yeah? So their baseline health status is already lower than those people that do not go to the hospital. Yeah? So these people in that group, they feel fine. There's no need to go to the hospital. The people in this group, they're really, really sick. They go to the hospital, and therefore their baseline health is different from their the non-treated group baseline health, and the selection bias will make the whole thing negative. Yeah? So kind of this is what we see in our raw data, that the people that are in a hospital have a lower health status than those that do not go to the hospital. Yeah? This is because like their baseline health status was different in the first place. Yeah? So the naive comparison does not help us here. A similar thing turns out to be the case when we look at the average treatment effect. Yeah, so kind of now we analyzed the naive comparison and related it to the average treatment effect on the treated. And now we look at the average treatment effect, and it turns out that this thing can be written like as the sum of these three terms, where only the first term can actually be observed. Yeah, so kind of here we have like the comparison. We look at the treated group, and actually, yes, we want to see the outcome on the treatment versus the non-treatment group. And we actually are interested in the outcome in the absence of treatment. And kind of like 2 and 3 are again the terms that we would like to get rid of. Here, again, we see we cannot observe this. We have the treated group, but we want to see kind of the outcome in the absence of treatment. This term cannot be observed. And then similarly here, yeah, so this plus this doesn't work, and this in this case doesn't work either. So 2 and 3 cannot be observed. And again, 2 and 3 are some sort of selection bias, right? So again, here we have the same thing that we have seen before, yeah, the selection term, yeah, where we may have differences in the baseline outcome, in the baseline health status, for instance, in the group that goes to the hospital and the group that stays out of the hospital. And the term 3 can be interpreted as it says here, the difference in outcome gains. Yeah? So we look at outcome gains between the treated group and the non-treated group. Yeah? So it could also be that in the people that go to the hospital, of course, the gain in hospitalization is higher than for the group that does not go to the hospital. Yeah? And this term, and then in that case, would be non-zero. Yeah. Okay. Now, what we see is that if these terms here, 2 and 3, are non-zero, we cannot identify the average treatment effect from the first line, which is the only thing that is observable. Okay, that's a problem. Just another example, which is going to be our running example. It's a job training to make this a little bit more economic. So we want to estimate the effect of a job training program, and we have a pool of unemployed individuals, and we tell them, okay, guys, look, you have the option to sign up for this job training program. And of course, you want to know what was the effect. So after 6 months, you go there and you say, okay, did you participate? What is your unemployment status? You collect the data, and you go to the other group and say, did you participate? What is your employment status? And then you simply do this comparison. And now you ask yourself, what are we actually measuring here? Are we trying to measure the treatment effect on the treated? Are we measuring the average treatment effect in the whole population? Or do we actually get anything sensible? Okay, now you think about this for a second and we continue talking about the benchmark, which is a randomized experiment. Okay, what do we do in randomized experiments? Well, as the name suggests, we assign the treatment randomly. Yeah. So for instance, DI is simply a coin flip, heads or tails. Yeah? So we have a group of people. First person comes in, I flip a coin, it comes out heads. You say, okay, you get the treatment. Next person comes, I throw the coin, tails. Okay, you don't get the treatment. And this is the way I assign the treatment group and the control group. And the big difference that this random assignment makes is that now the treatment indicator is independent of both potential outcomes. Yeah. So, right, there's like, since I don't even look at these people, I just flip a coin. It's completely independent. Okay. Now, why is this so important? Well, if you look at conditional expectations, then it turns out that if the Y, the outcome, the observed outcome, is independent from the treatment indicator, then this conditional expectation actually turns into an unconditional expectation. And the intuitive reason is that, well, because this thing, the DI, is independent from the YI, the DI does not give you any help in predicting the average of Y. It's completely useless. And therefore, you can just ignore it. That's what we say here. And now for our treatment effect estimation, if we again look at our selection bias, so that's equation 2, which we have seen here, this is the thing that we are looking at. If DI is independent of both, of actually like the potential outcome in the absence of treatment, as we assumed, then it turns out that I can replace this by this, because DI does not make any difference. The independence holds for any value that DI can take, and therefore I write this thing simply as the unconditional expectation, and therefore there's no difference anymore, and this becomes 0. And with a similar argument, we can show that the equation in 3 becomes 0. Yeah, so indeed, when we have a randomly assigned treatment, then what we can do is that we simply look at the first line. We just compare the treated group with the non-treated group. And it turns out that this identifies the average treatment effect, simply because we randomized. Yeah. Similarly, if we look at the average treatment effect on the treated, it's the same thing, right? So the average treatment effect on the treated is this. Now, DI equal to 1 doesn't matter. So this thing would simply be kind of like the expectation of YI1. Yeah, no, actually, let's look at this line. So kind of like the DI does not matter, and therefore, under randomization, the average treatment effect on the treated is the same as the average treatment effect. Yeah, so kind of we assume that this is a random sample from the population, and we randomize, and therefore they're both the same. Now, what is the intuition behind this randomization? Well, randomization makes sure that the treatment group and the control group are sort of comparable in large enough samples. Yeah, so kind of when I do this setup, so I let people come in, I throw the coin, and I say, okay, heads, treatment, tail, control. If I have a large enough sample, then there should be approximately the same number of females in the treatment and the control. Yeah, the age structure should also be similar here and here, because like each person with each characteristic has the same chance to end up in either of the groups. And if I have enough people, then the structure in both groups will be very similar. And what is the important part in statistical terms? Well, because both groups are the same, except for the treatment, right? So everything else is the same: age, gender, education, labor market experience, whatever, right? If you randomize, these things are on average balanced between the two groups. And this means that we have taken care for all confounding variables. Yeah, so we have two groups, and the only thing that is different between these two groups is actually the treatment. And this now traces back to our concept of causality, right? So two groups are exactly the same. The only thing that we change in one group is the treatment. And therefore, if we see a change in the outcome variable, because everything else is the same and only the treatment changes, it has to be the treatment that induces the change in the outcome variable. And this is what we call causality. Yeah, okay. Very important, if you use random assignment, then on average, the confounding variables in both groups, treatment and control, are balanced. Yeah, okay, so this is now randomized experiments, and now let's go back to regression models. Okay, so when we have a randomized experiments, we can actually simply compute the average treatment effect by comparing the average in a treatment group with the average in the control group. Yeah, so that is kind of what we saw here. Average in the treatment group versus average of the control is our average treatment effect. Okay. We can compute the same thing in a regression framework, and we will see that using regressions has certain advantages. Well, first of all, when you use a regression, you can just type this in Stata, and Stata will give you the standard errors, easy peasy. The next thing that is very, very important is that we can include additional variables, like additional control variables. And this is sometimes actually really, really important for your causal inference. And if you're not in a randomized experiment, as we will see later in the difference and difference, then because you use the regression framework, which you know very well, you know exactly what kind of conditions you need for consistency. Okay, now recall that we can write the observed outcome like this. Yeah? So let's write the linear regression model. So we have the outcome is written here as the intercept, the alpha, which is simply the expectation of yi0, the average outcome in the absence of treatment, plus here di is our explanatory variable, and the parameter that we are interested in is this rho. Rho measures the difference between the outcome under treatment versus the outcome in the absence of treatment. And then in order to make this equation hold, right, this has to boil down to this. We have to kind of write epsilon I as yi0 minus the expectation. Yeah, so this cancels with this, and indeed you go back to this equation. Yeah, so kind of like yi is expressed as yi0 plus this times this. Yeah, so indeed the equation holds. Yeah, so kind of if you have now a random sample from this experiment, you simply run this regression, and what you're interested in is your estimator of rho. Yeah, because yeah, okay, so let's talk about our regression framework versus what we just learned about random experiments. In regression, we always care about the exogeneity of the explanatory variables of our regressors. In this model, the only regressor is our treatment indicator. Yeah, so exogeneity means that if we condition on the treatment indicator, this has to be 0. Yeah, and now recall what was epsilon. Epsilon is this. Yeah. Now there's no randomness anymore in this thing. Yeah. So the expectation only applies to this. Sorry. And we see that, yes, we see that exogeneity holds if this thing here holds. Yeah. Kind of the condition expectation is the same as the unconditioned expectation. Plus, under exogeneity, we can identify our parameter of interest again as simply the average of the observed outcome in the treated group versus the average of the observed outcome in the non-treated group. How to see this? Well, okay, let's say di is equal to 1. What do we get? Well, we get alpha plus rho, and the condition expectation of epsilon is 0. So we get alpha plus rho minus, and here di is equal to 0. And there we only get alpha. So we get alpha plus rho minus alpha, which is the rho. So indeed, on the population level, our rho our treatment effect is again measured as, well, the average difference in the treated versus the average outcome in the non-treated. Moreover, notice that this equation 4, so exogeneity, is clearly true if the treatment is randomly assigned, right? So kind of we learned that if DI is independent of this, then the condition expectation boils down to be the unconditioned expectation. Yeah, so things make perfect sense here. So randomized experiments, writing as a regression, everything makes perfect sense. Everything fits together. Now, why do we do the regression framework? Why do we use it? Well, the important thing is that now we can plug in some additional X variables. And this can have multiple reasons, multiple advantages. The most important one is that sometimes your treatment, so exogeneity does not hold because the treatment is not independent from the potential outcomes. However, once you control for the X variables, the treatment indicator can be regarded as independent of the potential outcomes, right? So kind of like once you condition on X, meaning once you fix a particular characteristic, for all the people that have that characteristic, the treatment is randomly assigned. Yeah, so you see that kind of, if we have this condition, so conditioning, once we control for X, DI is independent of the potential outcomes, then we can write this here. Yeah, so we kind of compare the average outcome for all people that have a certain characteristic X, let's say, for instance, people that work in the same industry, and we compare the people within that industry that receive the treatment with the people within that industry that do not receive the treatment. Because the treatment indicator is independent of Y, once we condition on X, on the right-hand side, you see that the treatment indicator has vanished. Yeah? So we can identify this thing by just looking at the average outcome for the people, like the difference in outcomes for the people in the particular industry. Yeah, and that's what I mean here when I say we make an apples to apples comparison, right? So we kind of only look at the same in the people that have the same industry, and then within this industry, treatment is randomly assigned. Yeah, so we don't mix up, for instance, the IT industry with the construction industry, and we consider the same job training. That doesn't make sense. No, we have to consider the people that receive the job training within the same industry, because otherwise we have confounding variables. Like industry would be the confounding variables. Huh? People that work in IT tend to have higher salaries in any case, right? So that would be a confounder. Okay, so we condition on X, and once we control for X, the treatment is independent of the potential outcomes. Super important. And how do we recover the original average treatment effect? Well, again, we use the law of iterated expectations, right? We know that this thing here, when we condition on X, we can simply average across X. Yeah? And by the law of iterated expectation, this boils down to this thing here. Yeah? So we condition on X, and then when we want to recover the average treatment effect for basically the whole population, we have to average across all potential outcomes of the X variable. Okay, now here's an example. There is a famous paper by Kruger, and he studies a randomized experiments which looks at the effect of class size on learning outcomes of the students. And now the experiment was not carried out in a way that you look at the country and then you just randomize a couple of classes. Yeah? So kind of you randomly choose a couple of classes and make them smaller, but rather that you first went to a particular school, and then within that school, you randomized. Yeah? So kind of this school has, for instance, 20 classes, and you say, okay, I randomly choose 5, and those classes will have a reduced number of students. So the randomization is not done on the population level. Yeah. And of course, within school, there may be, or between schools, there may be certain differences. Yeah, so it does not make sense to treat this as a randomization on the population level, because there may be unobserved differences between the schools. Yeah. However, randomness holds within schools. Yeah, so kind of if you look at the particular school and you kind of look at the treated versus the non-treated, this kind of is randomized. Yeah, so here the confounding variables are balanced. So what Kruger does is that he conditions on school fixed effects, yeah? Because we have learned that when we condition on school fixed effects, we are actually looking at the within school variation. Yeah? So kind of if he conditions on school fixed effects, yeah, so our X variable here would be simply a school fixed effect, then we are comparing the treated versus the non-treated within the school. Yeah. And then in order to recover the treatment effect for the whole population, you do this for every school and you average across schools. Yeah. Okay, that is kind of the idea. So first important part, why would we condition on X? Well, random assignment holds only when we condition on the X variables. In this particular case, random assignment holds only when we include school fixed effects in the model. Now, there may be other reasons to put some additional information, X variables, in the model, even if you don't really need it to ensure random assignment. So X is not necessary for random assignment. However, if you include X in the regression, this typically improves the precision of the estimates, yeah, of the parameter that you're interested in. Yeah, so kind of like, let's say X is uncorrelated to the treatment indicator. Yeah? And therefore, if you kind of simply do not control for X, it doesn't matter for unbiasedness, right? So you don't have an omitted variable bias. However, if X is hidden in the epsilon, the variation that is in X is now variation of epsilon. Yeah? So kind of like variation that you in principle could observe now becomes unobserved variation. And this makes the signal to noise ratio worse. So whenever you have additional information, even if it doesn't help you to get like unbiased inference, you should nevertheless include it in order to kind of reduce the variance of the unobserved error, yeah? And therefore improve the precision of your estimator. So for instance, like in the Kruger paper, he controls for other variables, like whether the kids get free lunch or like the years of experience of the teacher. Yeah? Okay, so so a couple of last words about like these randomized experiments. So in the economic literature, they are called randomized controlled trials. Yeah, and these things have become really, really popular in recent years because like due to this randomization, they are by many people regarded as the gold standard in terms of credibility. So kind of because randomization automatically balances the confounding variables in the treatment and in the control, people argue that randomized control trials are very credible because we have taken out any confounding variable already by design. Moreover, like because you just do randomization, researchers pretty much do not have to make big choices. Yeah, so kind of like one researcher would make this choice, another researcher would make another choice. For randomized controlled trials, everything is so simple, right? You simply randomize and then you run a regression. You know exactly what to put. Yeah, every researcher would do the same thing. So the less choice that you have to make, yeah, the less kind of subjective choices that you have to make, the more credible is it, the more objective the final result becomes. Okay, now RCTs are regarded widely in the literature as gold standard. And in fact, you know, like not too long ago, Duflo and Banerjee, they got the Nobel Prize for this kind of stuff. So whenever you don't have randomized data, a reasonable idea is to look for situations where the treatment assignment is as good as random. Yeah? And this is what we're going to call a natural experiment in the second part of the lecture. Now, look, for instance, there's also, of course, as usual, people go crazy about RCTs. They say it's the best thing ever. However, there's also reasonable criticism of like these randomized control trials. And like a very nice paper if you're interested. There's also an article if you just Google it. There's like Angus Deaton and Nancy Cartwright, who have very reasonable criticism of RCTs. Yeah? And Angus Deaton is pretty well known. He also is a Nobel laureate. And the argument is pretty much that an RCT is not simply a magic bullet that solves every problem. Yeah? So simply having something unbiased, yeah, by running a randomized controlled trial in Kenya does not mean that taking the same idea and moving it to South America or maybe to Europe will also work. Yeah. Okay. Yeah, that's it for the randomized experiments. And now we talk about basically how to get as close to that as possible. But that's in the next part.